Okay, Chapter 7, Unit 7, I should say, Rational Expressions and Functions. This is the first video, 7.1a. We'll be doing the first half, 7.1 in this video. Unit 7 is about rational expressions, like I said, but it may as well be called fractions with variables. That's really all it is. A rational expression is a fraction with a variable in it, or more than one variable. So let's review a little bit. Rational numbers. A rational number is a quotient of two integers with the denominator not equal to 0. Okay, so things like 1/3 or 4/9 or 2/4, which we can reduce to 1/2, right? Or things like 56/10, things like that. Even whole numbers, 26/1 is a rational number, right? We know that we can simplify that to 26. So any integer over integer where the bottom number is not 0, right? Because this also means divided by. All of these are 1 divided by 3, 4 divided by 9, and we would never want to divide by 0. So we can have any fraction we want. We could even have 0 over 100, right? That's still an appropriate fraction. We just reduce it down to 0. Those are our rational numbers. As you can guess, rational expressions are virtually the same thing, except they have variables in them. That's all. That's the only difference. They just have variables in them. They can still have numbers. Most of them still do. Things like this negative a over the fourth, right? That's just got a variable in the numerator. You can have variables. You can have polynomials. Here we've got a binomial over a binomial. Here we've got a trinomial over a binomial. And then as expressed before, since we had 26/1, it's the same thing as 26. All of our regular polynomials, x to the 5th, are also rationals because they're just x to the 5th over 1, right? So things over 1 are also rationals. So anything that we've seen before has been a rational. It's just been a rational over 1. Now we're going into those ones that don't have, it's not over 1. They have something else on the bottom for the denominator. A more formal definition looks like this. P and Q are polynomials, so things like m plus 4 and m plus 2. And you've got P over Q such that, remember this little bar means such that, not anything too fanciful, just P over Q such that Q and P are polynomials and Q is not 0. So it's basically the same definition as a fraction, but instead of two integers, you've got two polynomials. Awesome. Now, like I said before, this chapter really should be called Fractions with Variables because there are so many different parallels between this and fractions, regular fractions that you dealt with before in 5th grade. So we're just going to draw a lot of parallels for that. Before, let's get a little practice on which one of these are actually rationals, right? So which one of these are actually rationals? Well, that would be a rational. We talked about that, right? That's 4x over 1. 4x over 2, definitely a rational expression. This one's also a rational expression, over 1. This one's also a rational expression, over 1. Oh, hold on. Just kidding. Not that one. We'll talk about this more at the end of Chapter 8. But this right here, excuse me, is an imaginary number. It is not real. Rationals do have to be real. So this would not be a rational expression. Square root of 45, that is, type that into the calculator, 6.700820 ... Because I had to ... that means that this is not equal to a fraction, right? So a non-terminating decimal, something like the square root of 45 that gives you something crazy and long like that, cannot be written as a rational. Things like the square root of 2, that's nice and easy. That's 4, or 4 over 1, right? I'm sorry, I said that backwards. My apologies. The square root of 4 is 2, or 2 over 1, which is rational. The square root of 5. Square root of 5. Nope, not square root of 5. Just kidding. That's non-terminating. Anyways, the whole numbers are definitely rationals, but things like square root of 45 would not be, because you cannot express them as a fraction, right? Okay. Defining a rational and determining its domain. So, rationals. Rational functions are just an extension of a rational, right? So instead of just a polynomial p, we actually have a function p of x over a function q of x, where q of x is not equal to 0. So again, it's the same definition. right? Same definition. But recall that functions are one-to-one. So if I plug in a value of x, if I make these both 1, I'm only going to get one answer back, right? So it's basically I can plug into these. We have to actually figure out if it's true. Here, that's a little tricky, right? Because q cannot equal 0. If we plug in an x and end up making q equal to 0, it's no longer a function. And that's an important distinction here. So functions must be one-to-one. One-to-one. They cannot have 0. So no 0 denominators. Let's check out a couple of these functions over here. We'll talk about those. Excuse me. And we will decide if they're functions or not. The best way to, we'll define their domains. Define their domains. What values would not make them functions, right? What values would not make their functions? So we can call this a function still as long as we say the domain cannot be something. Now what can the domain not be? That's probably easier than deciding what the domain can be. Remember, domain means all possible x's. Things that when I plug it in, I can actually solve for it, right? So which one of those would not be possible? What x here would cause a problem? Well, the x here causing a problem would be down here, right? First off, the x is only in the denominator. Starts off in the denominator, or it is in the denominator. And what value, if I plug that in there, would make this a problem? Remember, the problem would be is if that denominator equaled 0. So in other words, what value would make the denominator of x minus 5 equal 0? That's our question. What would that be? Well, it looks like the value, add 5 to both sides, x equals 5. That would be the problem. That would be our problem. So in other words, x minus 5 cannot equal 0, so x cannot equal 5. You see how that is? So the domain is everything but 5. So x such that x does not equal 5. That's our domain. 5 is the only one it is not allowed to be. Let's try that again with another problem. I've got g of x. Again, I've got a single number, an integer, over a polynomial that makes this a rational expression, right? A rational expression. A rational function. But there's some x that doesn't work here. What x is that supposed to be? Well, remember, the only problem is if the denominator is 0. So let's set this equal to 0 and see where our problem would lie. So at what point is x not equal to 0? So let's see. So I can add 14 to both sides. And I get 7x is equal to 14. Or divide by 7, x cannot equal 2. Right? And technically this is not equals, right? Because we don't want to say it can equal 2. It's the only thing it can't equal. If you don't like this cannot equal thing, that's fine. Just remember that what you're finding is the things that x can't be. Okay? So these x equaling 2 is a problem. That is the problem. So our domain would be x such that x does not equal 2. Otherwise, if I plug any other value in there, I can get a fraction, right? If I plug in, a 1, I get 7 minus 14, or g of 1 is equal to negative 3/7, right? So I can get a number out of that. That's the problem. That's the point. But if I were to plug in a 2 there, then I would say, okay, g of 2 is equal to 3 over 7 times 2 minus 14, right? Or 3 over 14 minus 14, 14 minus 14, or 3 over 0, and we now have a problem because you cannot divide 3 by 0. Like, what? You can't do that. So that would be the only one that doesn't work, right? Anything else would actually give me a number at the end, but I can't divide by 0. All right, let's do another one. I have this function here, h of x is equal to 4 over 4x minus 9, right? The only problem would be the denominator. Can't have that equaling 0, so let's figure out what x would make the denominator 0. Let's see. So in this case, I really don't want this expression that makes up the denominator equal to 0, so I'm going to figure out what that would be. I'll add 9 to both sides. I get 4x is equal to 9. Divide by 4, using my properties of equality, right? And then I get x is equal to 9/4. Or not equal to 9/4, right? That's the problem. So in this case, my domain is all x's, all possible x's in the universe except for 9/4. 9/4 causes a problem. Other than that, I can plug in 1,000,000, I can plug in 5,000, I can plug in negative 246, right? I can plug in negative 300 over 48, but I cannot plug in 9/4, otherwise that gives me a 0, and that's a problem. Okay, let's try another one. So those ones were pretty straightforward because all of the denominators were nice and linear, right? They were nice and linear. 4x minus 9, 7x minus 14, x minus 5, right? Very easy to solve. Now we've got r of x that says 3 plus x over x squared minus 4x plus 3. That's our rational function, okay? And remember, you can have any size polynomial in the numerator and the denominator. There's nothing wrong with that. You could have 4 terms in the denominator. You could have 5 terms in the denominator. The problem is this denominator can't equal 0, right? So it's got to be something where it does not equal 0. So let's see, this denominator is negative 4x plus 3, and we want to make sure that does not equal 0, right? Does not equal 0. I'm going to solve this like I would if it did equal 0. We just did that for, days in the last chapter, finding where x equals 0. So we're going to have 2 different answers here, right? This is a quadratic. We're going to have to factor it. So let's factor the left-hand side. Let's see. I don't see a GCF. I don't see any special case. So 2 numbers that multiply to 3 and add to negative 4. That would be, let's see, 1 and 4. In order to get a positive 3, the 1 would have to be negative. Alright, so those are my numbers. Now factor by grouping. X squared plus 4x minus x plus 3. I'm sorry, no, they wouldn't. Just kidding, because those numbers don't multiply. I did that backwards. Sorry, multiply to 3 and add to negative 4. That would not be 4 and negative 1. It would be negative 1 and negative 3, right? Negative 1 and negative 3. So plug those in. Minus 3x minus x plus 3 equals 0. Now I can factor by grouping. I get x minus 3. I'm taking the GCF of the left, this first group. GCF of the next group, well, they really don't have much in common, but I'm going to pull out that negative because I don't like negatives in front. I get x minus 3. And, okay, so now I can take out this common parentheses. X minus 3, x minus 1 equals 0. So, in other words, so I factored the left-hand side, right? So I used this little game, and then I used it to factor by grouping, undoing the multiplication, and then factoring by grouping, and I get x minus 3 times x minus 1 equals 0. Now, in order for that to be true, one of these has to equal 0, right? Zero product property, so either x cannot be, or x minus 3 can't be 0, x minus 1 can't be 0. Hold on, I'm going to write this just a little farther down. Because what I can do now is I can take this, I can rewrite it just for funsies, as x minus 3 and x minus 1. So when I factored this, I rewrote it as this. Now I'm going to come back to this part in just a minute, but I want you to see that these two are exactly the same thing. Now I'll use zero product property. It says, okay, if this cannot equal 0, then x cannot equal 3. And if this cannot equal 0, then x cannot equal 1. So those are the 2 answers that I am not allowed to have, right? Because both of those give me 0 in the denominator, right? Both of those, if I plug that in, would give me 0 for this big polynomial. Alrighty. So my final answer, the domain here, would be all the x's in the world such that x is not 1 or 3. So it can't be 1 and it can't be 3. That's my domain. Okay. Now, up here, when we did x minus 5, notice we just set the denominator equal to 0, right? Or we set it not equal to 0. We figured out that x cannot be 5. I did the same thing down here. I just had to get it into parentheses first. So if you don't want to set it up this way where you have this equal 0 the whole time, that's fine. But just know that every time you see a polynomial, you need to factor it into linears. Okay, so always start with factoring. Yeah, it's not going to go away. Sorry, we're going to use this the rest of the year. So start with factoring. Then see which ones they cannot equal, right? And then you get your domain. They cannot equal 0. Let's try that again. So I've got this s of x, 3x plus 1 over 2x squared plus x minus 6, right? Remember, the numerator is not a problem. You can have a 0 in the numerator. 0 over a billion or 0 over 100 is just equal to 0. That's a real number. That's okay, right? So it's okay if 3x plus 1 equals 0. That's fine. We don't care about that. We just can't have 0 down here, right? We cannot have 0 being the divisor, right? You can't take 15 things and divide them into 0 groups. That doesn't make any sense. So we're going to have to figure out when this thing ends up equaling 0, because that'll be the only thing that's not in our denominator. Alrighty. I'm going to put it in a little different of a form, though. I'm going to factor it first so that I can see maybe linearly what these answers are going to be. So I'm going to factor it. Let's factor it. We got 2x squared, let's see, plus x minus 6. Okay. I don't see a GCF. I don't see any special case because it's not square, so I'll just do general trinomials. Let's see, 2 times negative 6 is negative 12, adds to 1. Okay, negative 12 and multiplies to negative 12, adds to 1. What would those two be? Thinking 4 and 3 of some type. And I think to get a positive 1, it'd have to be a negative 3, right? So 4 times 3 would be negative 12. 4 plus 3 would be positive 1. Or 4 minus 3 would be positive 1. Alright, and then I'll take my polynomial. 2x squared sorry, let's write that a little better. 2x squared, instead of 1x, I'm going to write 4 x's and minus 3 x's. So that's that middle part I'm doing, 4 x's and minus 3 x's, and then I keep the minus 6. Now we'll factor by grouping. Okay, so I group the first two, group the last two. Excuse me. In the first two, it seems they have a 2 in common and an x in common, so I'll take out a 2x. What's left over is an x plus 2. In the last one, they have a minus 3 in common, so I'll take out a minus 3. I'm left over with x plus 2. And then now, one more time, they have an x plus 2 in common. I'm going to head... No, I don't know why I changed colors, my apologies. I'm going to head... yeah, I'll write it up here. So I have 2x plus 3 and x plus 2. So I took out the x plus 2, and I'm left with 2x, pardon me, minus 3, not plus 3. 2x minus 3. Alright, so I can rewrite this guy. Instead of what it looks like right now, I can rewrite it as 3x plus 1 over 2x minus 3 times x plus 2. I've factored the bottom, right? I factored the bottom. Now it's nice and linear, right? If it's linear, it's much easier to work with when I'm trying to find the domain, right? Because I can't have either one of these guys equal to 0. So I'll go over here and figure out what x's will do that. So that one can't equal 0, and that one can't equal 0. If this first one was to equal 0, I'd add 3 to both sides, right? 2x equals 3 divided by 2. Okay, so x is not allowed to equal 3 halves. That's my first part. And it looks like x cannot also be negative 2. So I subtract 2 from both sides to get x is negative 2. So my final domain is all the x's in the universe, every single one, except 3 halves and negative 2. Cannot be either one of those. If it was, we would get a 0 for one of these guys, and then we would get a 0 here, and so we get a 0 in the denominator, and the whole thing falls apart. We all cry and call it a day. So we don't want to have any 3 halves or negative 2's. Alright, so I hope this is starting to make a little sense. We're going to do one more. But basically, the concept is use your previous chapter tools, right? This isn't new. Factoring isn't new. Neither is solving. But you just don't want a 0 in the denominator, right? We've got denominators that we cannot have equal 0 now. So let's do one more. We've got t of x is equal to 2x squared minus 3x plus 4 over 3x squared plus 8. Now again, numerator. Not important, right? Because you can get that equal to 0. Numerator can be anything it wants to. Any number in the universe. Heck, it could be another fraction. We'll talk about that a little later in the chapter. But the numerator is not our important goal right now. It's the denominator. The denominator cannot be 0. We cannot divide by 0. So let's see what would do that. So it's a quadratic. We're still going to end up with 2 answers, right? However, we saw in the last chapter, no we didn't, we'll see in chapter 9 that you can solve this without factoring. Let's try it out. So let's try this out. Instead, let's solve this like it was linear. Let's pretend this part wasn't here. Because it doesn't have a middle term, I can do this. If it had an x, then I wouldn't be able to do this, right? If it had 3x squared plus 4x plus 8, that's a problem. Here it's just a 3x squared. So we're going to try and isolate the variable. Let's isolate the variable. Subtract 8 from both sides. You get 3x squared is equal to negative 8. 3x squared is equal to negative 8. Divide by 3. Divide by 3. Okay. And you get x squared is equal to negative 8/3. Now from here, I can take the square root of both sides. That's a property we will talk about a lot in chapter 8, but we'll use it here for just a moment. So x cannot equal the square root of negative 8/3. Is x going to ever equal the square root of negative 8/3? Probably not. So this is our technical answer, but that's not even a real number, and functions only deal with a real number. So what this is saying is this is an infinite domain. All real numbers are possible here. You can't have a negative under the radical. Since having a negative under the radical is the only case that would give us 0, it doesn't matter, right? It doesn't matter. Since x is squared here, and there's no other x's involved, this doesn't have an x that would cause a problem. So this is more of a concept problem. So this is not real, right? And just because I say not real, it doesn't mean it's fictional. It means it's imaginary, right? We'll talk about imaginaries again at the end of this chapter, next chapter. So the domain here would be x such that x is all real numbers, and that's the way you can write all real numbers. You're more than welcome to use the English. Please use the English if you want to. If you know what this notation means, that's fine. But the point is it's also all reals, okay? That would be our domain. All real numbers. Nothing here would cause a problem because everything would be squared, right? So the bottom was always never going to be 0. Nothing here would ever give us negative 8. Alrighty, so that's domain. That's domain. Use other tools and you'll be fine. Our next objective is about writing these rationals in lowest terms, okay? So until we get there, just recall domains cannot be 0, right? Sorry, as you can tell, I have a bit of a cough. Alright, recall, fractions are just numbers that can be simplified by reducing to lowest terms, right? So if you have things like 15/20ths, well, you can reduce this. That's the same thing as having, a pie of, let's see. So you've got this pie, right? And you've got 20 different slices. Let's see, that's 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. 5, 1, 2, 3, 4, 5, right? And you've got 15 of them, right? Here's 15. You've got the same thing as 3/4, right? So remember, fractions are pieces of the whole. They're pieces of the whole. It's part over whole. So if I want to take this fraction that's divided into many, many itty-bitty little pieces, and I want to make it into something a little smaller, I just have to find a common factor between here and here. So a common factor between 15 and 20. Well, 15 has 1, 3, 5, and 15. This one's got 1, 2, and 10, 3, and 3, no, not 3, sorry. 4, and 5, and 10, and 20. Okay, so it looks like they have 5 in common, right? They have a 5 in common. So I'm going to divide, I'm going to divide each by 5. Divide by 5, divide by 5. I end up getting 3/4, which is just like what my picture said. So just find a common factor and take it out. Divide by, what you're essentially doing is dividing by 1, right? Dividing by 5 over 5, which gives you 3/4. Let's do the same thing over here. 49 90ths. 49 90ths, well, 45 and 90 both have what is a common factor. They definitely have 5, right? So we can take out a 5. You get 9 over 10. No, you don't. Yeah, you do. 9 over 10. Fabulous. 9 over 10 has nothing else in common, right? So that was dividing by 5 again. Or sorry, dividing by 5 over 5. And then in the last one, 67 over 125. Well, 67 is actually prime, isn't it? Yep, 67 is prime, and so it can't. The only factors it's going to have are 1 and 67. So unless 67 goes into 125, which I strongly believe it doesn't. Yep, well 67 is divided by, or 125 divided by 67 is 1.856. So since these share no factors other than 1, this is what we call reduced, simplified into lowest terms. Alrighty. So lowest terms means that the top and the bottom have nothing else in common, right? And sometimes it's not going to be nice, tiny little numbers, but they have nothing else in common. That's all for rational numbers, okay? So those are for fractions. The same logic, though, applies for rationals. The same exact logic. If they share something in the top and the bottom, then you can cut it out. You can cut it out. Another way to think about this one, just before we move on to there, is if I've got 45, well, that's the same thing as 9 times 5. And here I've got 90, which is the same thing as 9 times 10. I think I did this one wrong. Yeah, my apologies. I did this one wrong. Okay, let's try this one again. I don't know why I was dividing by 9 and then 5. Okay, let's try this one again. Let's think about this one because I was going to go back and redo this anyways. So 45 is 9 times 5, right? And 90 is 9 times 10. Cut those down, and you've got 5 tenths. Sorry, it should have been 5 tenths. I was wondering why that worked out a little too easy. Then here, what do 5 and 10 have in common? Well, this is 5 times 1, and this is 5 times 2. You've got 5 over 5, which is equal to 1, and you get 1 over 2. 1 and 2 are both prime, so that's all they have, right? So they've got 1/2 as the final answer. I don't know where 9 tenths came from. My apologies. So 1/2 is final answer. But this is another way to think about it. You can split it into factors and then cancel out those factors. I highly recommend this way because when you're dealing with rationals, that's essentially what we're going to be doing. We break it down into lowest factored form. So numerator is factored form, denominator is factored form, and then you go a canceling. If I have an x plus 2 on the bottom and an x plus 2 on the top, then I can cancel them. In other words, what I have is x plus 2 times x plus 5. I just switched the 2 in the numerator. I'm going to keep the denominator exactly the same because then I notice these two are exactly the same. The top and the bottom, these two are exactly the same, right? So essentially I have x plus 2 over x plus 2. They cancel each other out by quotient rule. Really? And what I'm left with is x plus 5 over x minus 3. That's my final answer. Now be super, super careful. Because the x is adding to 5 and the x is subtracting 3, these two x's do not cancel. Okay, you can only do this with things being multiplied. Every single one of our fractions were being multiplied, right? 5 times 1, 5 times 9, right? So they were being multiplied. Same concept here. X plus 2 times x minus 5. X plus 2 times x minus 3. That's why they canceled, because that doesn't violate PEMDAS. I can't cancel the x's because one's being added and one's being subtracted to a different number. Okay, so this is actually as far as this rational will reduce. Excuse me. Alrighty, let's keep going. I've got these two guys. Right now, there is nothing I can cancel. Right, I can't go canceling p's and q's because they're all being added or subtracted. Excuse me. However, these are not in final factored form. So let's look at the numerator first. Whoops. This guy. Let's see if we can simplify him a little bit. So we've got PR plus QR plus PS plus QS. The fact that there's 4 terms here just screams factoring by grouping. So let's group. Group these two guys, group those two guys. In this first one, I can take out an R. I get P plus Q. In this second one, I could take out an S. plus s. And I'm left over with p plus q. Now they've got a p plus q in common. I end up with p plus q times r plus s. Alright, so that's a new way to write my numerator. My numerator now becomes p plus q and r plus s, right? That looks a lot better. Now I've got some things actually multiplying, right? So maybe if we do the same thing with the bottom, the denominator, we might get some things that'll cancel. So this one, let's do this one in pink. This one is p plus r. Oh, sorry, not p plus r. It's pr plus qr minus ps minus qs. So very, very similar to the numerator, right? But I don't want to cancel it as is. I can't cancel prs and qrs because those are being added to other things, right? They have to be being multiplied. But let's go with grouping here. Let's group those guys. I get, okay, here they have an r in common. P plus q is left over. Here they not only have an s in common, they actually have a negative sign in common, so we'll do minus s, p plus q, and now they've got a p plus q in common. So we'll take that out, and what's left over is an r minus s. Now, if what I'm doing right now is complete gibberish to you, you have no idea what I'm talking about, you need to go back to chapter 6, and you need to review your factoring, okay? So you need to review the factoring by grouping video, 6.1. Yep, 6.1, maybe 6.2. And you need to review factoring trinomials, okay, 6.2, that's 6.2. 6.1 and 6.2, you're going to need to review for this chapter if you don't remember how to do them, okay? Alrighty, so this is the new denominator. We have p plus q times r minus s. P plus q times r minus s. Alrighty, now I'm definitely seeing some things I can cancel, right? I can cancel a p plus q and a p plus q. Those are identical parentheses, so those parentheses definitely cancel. I can't cancel the other ones, even though they're both r's and s's, because one's being added and one's being subtracted, and that kind of sucks, but it leads me to my final answer of r plus s over r minus s. That's my final answer. That's my reduced form of irrational. Cool. And again, essentially what we did was we, quote unquote, pulled out a 5, right? We pulled out a 9. Here it was 9 times 5. We just rewrote it as, or we rewrote 45 as 9 times 5. Here we rewrote this horrible thing as those two things being multiplied, right? So you just changed it so that you're multiplying stuff, and then you can cancel. You get r plus s over r minus s. All right, let's try another one. Here's D. Oh, yay, some more factoring. Again, I can't cancel anything right now because they're all being added and subtracted. I can't cancel addition and subtraction. It doesn't work like that. So I'm going to have to factor both of these. Factor the top one. So let's see. A squared minus a minus 6. A squared minus a minus 6. Okay, I've got two numbers that multiply to negative 6 and add to negative 1. Two numbers that would multiply to negative 6 and add to negative 1. Well, let's see. 2 and 3 sound pretty good. 2 and 3 sound pretty good. In order to get a negative 6, one of them would have to be negative. In order to get a negative 1, that'd have to be a negative 3. So negative 3 times 2 would be a negative 6. Negative 3 plus 2 would be a negative 1. Got a squared minus 3a minus 2a, plus 2a. Plus 2a minus 6. Once again, I've split up the middle. Now factor by grouping. Here they have an a in common. A minus 3 is left over. Here they have a plus 2 in common. A minus 3 is left over. I end up with a minus 3 times a plus 2. So my numerator is now a minus 3 times a plus 2. Sorry about that little extra minus there. It should just be minus. Alright, so that is my new numerator. Awesome. Now we'll do the same thing to the denominator. Same thing to the denominator. I have a squared plus 5a plus 6. A squared plus 5a plus 6. Let's see, two numbers that would add to 5 multiply to 6. That looks like a positive 2 and a positive 3. So I will split that up as such. Instead of 5, I'll write 2 and 3. Factor by grouping. What's left over is a plus, oops, I'm so sorry. When I take out an a, I'm left with a plus 2. Here I take out a positive 3, I'm left with a plus 2. And I get a plus 3 times a plus 2. So my new denominator would be a plus 3 times a plus 2. That looks much more workable for canceling, right? This, not so much, not so easy to cancel. This one, though, definitely easy to cancel because I can see a plus 2 cancels with a plus 2. And my final factored form, I'm sorry, my final reduced form, let's put it in green, would be a minus 3 over a plus 3. And that's it. Awesome. Let's try another one. Alright, again, I can't go canceling y's and 4's because they're being added subtracted. Let's see if we can maybe reduce this a little bit. A squared minus 4, or sorry, y squared minus 4. Interesting. I don't see a GCF, but I do see a special case here. Here's a square, and they're being subtracted. Check that out. It's difference of squares. So this I know factors to y plus 2, y minus 2. If you didn't quite remember that, you need to go back and check out 6.3 because that's special cases, okay? Lucky for us. Okay, so the bottom, well, let's do the same thing. So that was pretty easy. I remembered my special case. I didn't have to do this whole factoring steps thing. I could just use the special case, right? If I didn't, though, I could throw a 0 in the middle of that and it would still work. Alright, next one, 2y minus 4. Oh, sorry, plus 4. That one's already linear. That's awesome. It doesn't match any of my other things, though. So, what can I do? Well, I do see a GCF. Let me take out that GCF. If I do, I get 2 times y plus 2, right? Not the most fancy reduction in the book, but that's okay. I get 2 and y plus 2. Alright, and notice that helped me out because these two now cancel. And my final factored form, I keep saying final factored form, my apologies. My final reduced form would be y minus 2 over 2. That would be my final reduced form for this guy. So notice that the game goes like this. You need to reduce these things down individually. Numerator, get it reduced into some sort of factored form. Denominator, get it reduced into some factored form, whether that's through trinomials or through GCF or difference of squares, whatever you need to get it down so that you can actually start canceling stuff. Once you have both factored forms, see what cancels. Not everything's going to cancel all the time, but always see what does cancel, and what you're left with will be your final reduced form. Let's try another one. 8 plus k over 16. Well, remember, I can't cancel things that are being added or subtracted. So even though this is being added or subtracted, I can't just willy-nilly cancel away, right? There's one other thing I could do, though. I could rewrite this into separate fractions. It's a little cheater's way. This isn't the most ideal. We actually do want to keep things in one fraction if you can. But if you needed to split it up, you could split it up like this, and then you could reduce the first one to 1/2 plus k over 16. Where you would need this, honestly, I don't know. So if you wanted to just call this simplified form, you would not be wrong. You would not be wrong. However, another way you might see it would be something like that, where you split up the fraction. Cool. But the main point here is that you cannot, this would definitely not reduce down to 1 plus k over 2. Okay, this is not equal to 1 plus k over 2. The k is being added there. It's not a separate entity, okay? So this is not right. Alright, next one. M minus 3 over 3 minus m. Again, I can't just start canceling stuff. These are not the same, right? This is not the same. Now, a little side note. If I had the case of 3 plus m over m plus 3, whoops. So notice this time it's addition. Would those be the same? Yes, they would, right? Because the commutative property, right? I can rewrite this as m plus 3 over m plus 3, and they would cancel down to 1, right? That would be the same. But remember, commutative property doesn't apply to subtraction. 2 minus 3 is not the same thing as 3 minus 2, right? So, I can't just say this is 1. This is definitely not equal to 1. There is something else I can do, though. I'm going to take the top one, and I'm going to pull out a negative 1. And I get m, no I don't. I get negative m plus 3, right, over 3 minus m. And then if I switch those two, because now it's addition, now it's commutative, right, now I can flip it around. I get negative 1 is 3 minus m over 3 minus m. And now suddenly things cancel. And I'm left with negative 1 over 1 or negative 1. So don't think that there's nothing you can do in this case, right? There's not nothing you can do, but it's just not commutative property. You have to take one extra step and actually pull out a negative to apply the commutative property, okay? So not everything's going to be factoring, but again, the game is get it so something matches if you can, and then cancel them, right? Cancel what you can that matches. Let's do one more, last one. Last one for section 7.0a. I've got r squared minus 16 over 4 minus r. Let's, again, start with the numerator. Start with the numerator. R squared minus 16. Very similar to what we saw with that problem with the y's, right? I've got a square, they're being subtracted, it's difference of squares. So I know this factors down into r plus 4, r minus 4. Alright, so that's my new numerator. My denominator is 4 minus r. Now again, be very careful. That is not the same thing as r minus 4, right? That is 4 minus r. But we just saw how to change that. We can rewrite this as negative 1 times r minus 4. We can flip it around. Right? So I can rewrite it as negative 1 times negative 4 plus r, right? Switch the signs. And then I can flip them around, and I get r minus 4. And I wanted to do that so that these two guys would cancel. Boop. I'm left with r plus 4 over negative 1. And remember, the way back into those fractions, if you have a negative 1 on the bottom, that's the same thing as you can pull that to the outside. So you have r plus 4 over 1, or in other words, negative r plus 4, or negative r minus 4, as the final answer. Or negative 4 minus r, it really doesn't matter. You can switch those around because they're both negative. Alright, so we've talked about 2 whole things in this chapter, 2 whole new things. 3 whole things, actually. What is a rational? Right? What is a rational expression? It's a fraction containing polynomials, right? And in order for that to work, they cannot have a domain of 0. And how can you reduce them? You can reduce them by factoring each one separately. Deal with a numerator, then deal with a denominator. If you try to do both at the same time, your head's going to explode, okay? So deal with one, deal with the other, then see what cancels, okay? It's just a 3-step problem. It's 3 steps. Deal with one, deal with the other, then reduce. That's all it is. Alright, and you can see you can use a multitude of tools in order to reduce them. Objective 4 and 5 are multiplying and dividing rational expressions. We will do that in the next video. So if that's what you're looking for, go ahead and head to the next video now.